Once again, my warm regards to you as we meet for this lesson today. Our lesson today is on nonlinear regression models. Our emphasis so far has been on linear regression models, but at times we may be forced to consider fitting nonlinear models. In this topic, we take a look at some of the basic nonlinear regression models that we use. Models can be nonlinear in parameter or variables and are classified as intrinsically linear or intrinsically nonlinear. Intrinsically nonlinear models are models that cannot be transformed to linear form through any transformation, while intrinsically linear models are those that can be transformed to linear form through some transformation. Some models that are nonlinear in parameters cannot be transformed to linear form and are therefore intrinsically nonlinear. Moreover, for such models, the parameters cannot be estimated using ordinary least squares method. For example, if we look at this equation, the parameters are beta naught and beta 1. Beta 1 is in the power of e, and therefore it is nonlinear because if you write it, it will be e raised to beta 1. And then we have got an addition here for the error term. And this model cannot be transformed to linear form because of the addition of this linear term. So even if we transformed using the log transformation, what we get is this one. And we cannot simplify this part further than this because this is the log of a sum which cannot be simplified further than that. In most cases, nonlinearity in variables can be removed through transformations. For example, consider a nonlinear model in increasing powers of x. This is known as a polynomial model. It can be transformed by letting the powers of x to be equal to some variable z. So we can put x r1i to be equal to z1i, x1i squared to be equal to z2i, and so on and so forth. And we have got x1i power k to be equal to zki. And so our equation will be reduced to yi equal to this model. And you can see this is a linear equation, a linear model, which we can now use our data to estimate the parameters beta naught, beta 1, beta 2, up to beta k. Another example is when the dependent variable is related to the reciprocal of the independent variable. So you will see this is your dependent variable, independent variable, and you can see the slope is not linear. You can see it is non-linear. Now in this case, such a model can be represented by this equation. And you will notice now that the values of y are related to the reciprocal values of x. This is a nonlinear model, and we can transform it to linear form by letting 1 over x to be equal to zi. And when we replace 1 over x here with zi, the resulting equation that we have is this one, which is a linear model. We also have nonlinear models where the predictor variable is in the power, and like this, x is in the power of e. This is a nonlinear model. In order to transform such a model, we use the logarithms, taking the logarithm on both sides. Recall this, that the logarithm of e raised to power x is simply equal to x. So if we take the logarithm of our model here, this one, on both sides we take the logarithm, then what we shall have is log yi equal to b naught plus beta 1 xi plus ei. Notice now that our right hand side of the equation we have a linear form, and on this side we have the natural logarithm of y. So this is known as a log linear model because the predictor is in logarithm and the response is in logarithm and the predictor is in linear form. Another example of a nonlinear model is the case where we regress the logarithm of the response against the logarithm of the predictor. Let's consider the Cobb-Douglas production function, which is in this form. This model is nonlinear. You will see that the coefficients beta naught and beta 1 are in the power of x. And actually, even the error term is in the power of e. So this is a nonlinear model where y is the output, x1 is the labor input, and x2 is the capital input. So to transform this model to linear form, we take the natural logarithms on both sides. And this is what we get when we take the natural logarithms. So now you'll see you've got the ln of y and the ln of x1, ln of x2. So now, in this case, the model is in linear form in terms of the logarithms. And we can simplify slightly and write this one as alpha b1 log of x1 and log of x2 plus the error term. So this one here gives us the log linear model where alpha is going to be equal to ln beta naught, and we can compute beta naught from alpha by taking beta naught to be equal to e raised to alpha. So this is known as the double log model. Let's consider another form of nonlinearity that usually is encountered in econometrics. Consider a model of this form where now yi is equal to 1 over 1 plus e raised to beta naught plus beta 1 xi plus some error term. So you will notice that this component is actually nonlinear in two ways, that the predictor is in the power of e and also that it is in the numerator. So if we want to transform this model, it may take a few steps to do that. We start by inverting the model. So you take the reciprocal of yi, and this is what you get when you take that. Then you subtract 1 on both sides to end up with this model. After that, you simplify a bit on the right hand side, on both sides, and you simplify, and this is what you get when you simplify and put the left hand side at a common denominator. Now you can take the logarithm on both sides, and if you take the log on both sides, this is what you get. And you will notice this time now you have a linear form on the right hand side, and on the left hand side you have a log form. This looks like a log linear model, but it is not called a log linear model because of the various steps that we have seen, that we have gone through to come to this point. It is known as a logistic regression model. It is used when the response variable is dichotomous. That means that the response variable can only take a value of 0 or 1. Let's consider some interpretation of non-linear models that are linearized using logarithms. We start with the interpretation of a log linear model, which has this form. So when you do the transformation, the relationship between the logarithm of y and x is linear. As you will see here, it is linear. So how do we interpret this coefficient here? This means that 1 unit change in x leads to 100 into bracket e raised to beta 1 minus 1 percentage change in y. Notice that the change in y is expressed as a percentage of the unit change in x for the log linear model. Let us now consider the log linear model. The log linear model has the form yi equal to beta naught plus beta 1 ln xi, now plus the error term. Now the predictor is the one that is in the logarithm form. So after transformation, this transformation, the result that you get is a straight line, as you will see. When you plot y against the logarithm of x. So how do we interpret the coefficient? This means that 1% increase in x will lead to 0.01 times beta 1 units change in y. Notice that in this case, the change in y is in units because y is not in logarithm form. Let's now consider the interpretation of the double log model's coefficients. For the double log model, we have the response and the predictor variables in log form. So if we plot the graph for log y against the log of x, we will get a straight line, as you can see. Now, how do we interpret beta 1? Beta 1 gives us the elasticity of y with respect to x, and it is interpreted to mean that 1% increase in x will lead to beta 1% change in y. We shall illustrate our discussion with two examples, one where we fit the Cope-Douglas model to some data from Taiwan, and the other one where we fit a lean log model to household expenditure data. This will be presented in a separate clip, which will be shared on Google Drive, and you can use it to see how we use data now to fit these models. Otherwise, have a good day and thank you for paying attention. Bye-bye.